Thank you, Eduardo. So let us continue. And the next speaker is Giusi Capobianco from the University of Roma Tor Vergata. And she's going to talk about on the degree of the tropical one-fold Abel-Prym map.
Okay, can you hear me? Okay.
You don't have the microphone?
Is it on? Okay. Thank you so much for giving me the opportunity to speak here. I will talk about the joint work with Yoav Len on the degree of the tropical one-fold Abel-Prym map. I will give you some introduction and definition of weighted metric graphs, double covers of hyperelliptic graphs. I will give you a construction of 3 double covers of hyperelliptic graphs, and then talk about the one-fold Abel-Prym map and its degree. So let's start with the graph. So we will always consider V the set of vertices and E the set of edges. A metric graph will be a graph with a length function on the edges. And I will also consider a weighted metric graph, so there is a weighted function on the vertices. And gamma will be the tuple GLW. The genus will be the first Betti number plus the sum of the weights in the vertices. And I will now talk about hyperelliptic graphs. I'm not stating the definition of a hyperelliptic graph because it involves the divisor theory on graphs, but I will give this definition / theorem. If we consider a weighted metric graph with no points of valency 1, the genus at least 2, then gamma is hyperelliptic if and only if there exists an involution on the graph, length-preserving involution, such that it fixes every vertex of positive weight, fixes pointwise the bridge, and the quotient is a 3. And I will give you also some examples. For instance, these 2 graphs are hyperelliptic metric graphs. The one on the left doesn't have vertices of positive weight. And for me today, I will denote by the positive number on the vertex whenever I have positive vertex. And so if I don't have any positive number, you can think of it as a weight function identically 0. And I'm saying that these 2 are hyperelliptic, and the involution is this one that folds the graph in half. For instance, in the first picture, we have the 3. And in the second picture, you can see that the vertex of positive weight and also the bridge are fixed pointwise by this hyperelliptic involution. And as a consequence of the tropical Riemann-Hurwitz formula, we have that if we consider a 2-edge connected graph, so we don't consider bridges because we know that now we have infinitely many fixed points on the bridge, we can have actually a number of fixed points, and the number is B1, so if the first Betti number plus 1. So usually it's G plus 1, but we also have weights in the vertices, so it will be B1 plus 1. And in the first example, you can see that the number is exactly 4. And in the second one, if we contract the bridge, we just have 2 fixed points. And I will now talk about double covers of metric graphs. And today we will talk about unramified harmonic double covers, both dilated and free double covers. The definition for a free double cover is a harmonic morphism of degree 2 that is an isometry of metric spaces. And you can think of it as the preimage of every point consists of exactly 2 distinct points. And I will call them P and iota P, where iota is the involution on gamma tilde that swaps the 2 points in the fiber of 1 point. And a dilated double cover will be a weighted harmonic morphism of degree 2. Sorry, I don't have the time to define the weighted harmonic morphism, but I will give you an example. And we will call gamma dil the set of all the points that have just 1 preimage. So in the free case, we always have 2 preimages. In the dilated case, we can have points with just 1 preimage, but with a dilation factor that I will tell you. And since we are dealing with unramified covers, the genus of gamma will be always 2 to the genus of the target graph minus 1. For instance, this is an example of a free double cover of the Dunbar graph. You can see here that we have 2 preimages for each edge. And the loop, I decide to connect it in this way. So we have 2 preimages of the loop. And this is an example of a weighted, dilated double cover of a genus 7 metric graph. So you can see here that the thickness is the gamma deal, so is the set of points that have only one preimage. And we will give them a multiplicity, which is in this case 2, because we consider double covers. And whenever we have a weight function on the target curve, we can recover the weight function on the source curve by the harmonicity formula. And if the vertex is not dilated, then the weight will be the same on the two preimages, as in the case 2, 2, 2. But if the vertex is dilated, then we have this formula to compute the weight upstairs. And ED is the number of dilated edges incident to V. So you can check that if we don't have dilated edges on top, we have this formula, and here is the same. So here we have two dilated edges, and this vertex has weight 4, covering a weight 2 component. And I will now talk about just free double covers, and this is joint with Yov. We gave a construction of hyperelliptic graphs that are double covers. Let's take two edge-connected hyperelliptic metric graphs. I told you that now we have a finite number of fixed points. And I told you that the quotient is 3. And the number of fixed points is exactly the G+1 leaves of the graph. I will give you an example. For instance, I will consider this genus 3 metric graph. And the quotient will be 2 copies of the same tree that I will call T and T prime. And we have exactly G+1 leaves, V naught, VG, V naught prime, and VG prime. And those are the fixed points of the hyperelliptic involution. How do we construct a free double cover of this graph? We take 2 copies of each tree, like this, because we have to have exactly 2 distinct copies of any point. So given T and T prime, we construct T tilde plus and T tilde minus, T tilde prime plus, T tilde prime minus. And now we just have to decide how to connect the 2 preimages of the fixed points. So an example will be this one. Imagine these red edges as length 0. It's just for visualization. So I told you that here we have a quotient, so these lengths are not visible after contracting these edges. So upstairs, we can either connect them by switch them from the plus part and the minus part, or we can connect them inside. And all the possible combinations of this connection will give us all the possible double covers of this hyperelliptic graph. And as a fact that is easy to prove is that if we start with a hyperelliptic graph, then the target graph will be also hyperelliptic for double covers. But the contrary doesn't always hold. And we have this proposition that if we consider free double cover, where now the target curve is hyperelliptic graph, target graph is hyperelliptic, then this was already proved by Len and Zakharov. Then the number of connected double covers is 2 to the G minus 1, up to isomorphism. But we gave a different proof by using the construction of the hyperelliptic covers. And we proved that up to, out of 2 to the G minus 1, we just have G plus 1 covers, such that also the source curve is hyperelliptic. So a proof of the part B. If we consider J and J tilde the hyperelliptic involutions on gamma and gamma tilde respectively, we proved that there exists exactly one point in gamma, which is fixed by the involution on gamma, such that the preimages are exchanged, so they are not fixed by J tilde. So we can construct a double cover, and for each fixed point, we have exactly one double cover, which is hyperelliptic. And for instance, this is an example where the source curve is not hyperelliptic. You can check that we don't have a quotient such that we don't have an involution such that the quotient is a 3. But you see that the target curve is a chain of loops, so it's hyperelliptic. Yeah, here we also have a length function on the edges, but And now I will talk about the Abel-Prym map and the degree of this map, and I will introduce these objects, but I don't have time to explain. So the Jacobian of the graph is the set of divisors modulo linear equivalence of divisors. You can think of it as the Dar's burning algorithm and chip firing on the divisors. And the Prym variety is the kernel of the map that goes from the Jacobian of gamma tilde to the Jacobian of gamma, sending the divisor class on gamma tilde to the image in gamma. So we can define the one-fold Abel-Prym map, and it goes from gamma tilde to the Prym and sends 1 point to the class of divisors linearly equivalent to p minus iota p. Iota is the involution that swaps the 2 points. And as a remark, the Jacobian and the Prym are isomorphic to real tori with integral structure. The dimension of the Jacobian is G, and the Prym variety is G minus 1. And this G is the genus of the graph gamma that we have as a target graph. And as a theorem, we have in the free double cover case of metric graphs that if gamma tilde is hyperelliptic, then the Abel-Prym map is a harmonic morphism of degree 2. The contrary doesn't always hold. We have that if the Abel-Prym map is a finite harmonic morphism, then gamma tilde is hyperelliptic. And in the algebraic case, we have, if we consider an étale double cover of curves, C tilde is hyperelliptic if and only if the Abel-Prym map has degree 2. So here we have, it's not the same as in the algebra setting. And this is a counterexample. For instance, here, I didn't say that finite means that the Abel-Prym map has not infinite, the fiber is not infinite on some points. For instance, we proved that on the bridges and on the central part of the graph, the Abel-Prym map is infinite. Indeed, everything gets contracted to 1 point. And the gamma tilde is not hyperelliptic, but we can check that after contracting this part, we have a harmonic morphism of degree 2. Unless, we have to contract it, so we get a picture of this. Where here we have 1. And this is the double cover. And we can check that now the map is a harmonic morphism of degree 2, even though we didn't start with a hyperelliptic graph. And as a corollary, we have that if gamma tilde is hyperelliptic, then the image is a hyperelliptic metric graph of genus G minus 1. And the Jacobian of the image is isomorphic as principally polarized tropical Abelian variety to the Prym variety of the cover that we started with. And this is exactly the case also in algebraic geometry. So Birkenau and Lange proved that the image of a smooth curve, hyperelliptic smooth curve, is again a hyperelliptic curve of genus G minus 1, and the Prym and the Jacobians are isomorphic. And this is an example of what happens. So we have a double cover of dumbbell graph. The loop will have these 2 copies. And the Abel-Prym map identifies these 2 copies. And you can think of this as the same length of this. And the 2 preimages of the bridge get stretched by a factor of 2. So you can check that on the vertices, the map is a harmonic morphism of degree 2. And you can also check that the Jacobian is isomorphic to the Prym. And as a work in progress, I'm now working on the weighted and dilated case in the hyperelliptic setting. So if we have a dilated double cover and gamma is a weighted hyperelliptic graph, and we consider gamma dil the set of points where the preimage is dilated, and we consider only dilated vertices, we don't have dilated edges, then there exists a unique cover such that also the source graph is hyperelliptic, if and only if the dilation subgraph is connected after contracting the bridges of the graph. So when we have 2 edge connected case, the gamma dil has to be connected. And as a sketch of proof, we always use we contract the bridges, and we use Riemann-Hurwitz formula in order to relate the fixed points of the hyperelliptic involution on the two graphs. And this is an example where we have two dilated isolated vertices, but when we contract the bridges, we have just one component. And this is a hyperelliptic cover, is a cover of hyperelliptic graphs. And as a remark, when the dilation cycle is not connected, there are two definitions of the Prym, the continuous Prym and the divisorial Prym. And the continuous Prym works well in the context of moduli space. So when we have this kind of situation, we have to adjust the definitions. We have to extend also the definition of the Abel-Prym map in the weighted case. And what I'm now working on is trying to look at the extension of the Prym Torelli, maybe to some toroidal compactification, so yeah, in the hyperelliptic setting. Okay, thank you.